Thank you very much for coming today. I'm very sorry to be late. Although we have prepared the connection 2 hours before following their request, but it didn't work now. So it is my great pleasure to introduce Professor Pieter Dorenbos, Professor of Delft University of Technology. He is a world-famous expert on solid-state physics of inorganic phosphor materials. I just briefly introduced his CV. He was born 5 years before myself in north part of Netherlands. And he graduated University of Groningen and finished PhD course there and starting assistant professorship at Delft University of Technology at 1989. And he became associate professor, promoted, and starting full professorship since 2008. He has been many achievements of solid-state physics of inorganic phosphor material, which is now widely used for white LED, scintillator of radiation detectors, and long persistent phosphor materials. He has many publications, more than 300, and many of them are cited more than 100, 200, 400 times. Totally, he has more than 7,000 citations in the world. So he's really world-famous scientist in the field of luminescent materials. So today, he will talk about luminescence in science and society for the general audience as an international seminar of our graduate school of human and environment studies. So please.
Thank you very much for this nice introduction, Professor Tanabe. It's really my pleasure to be here today and to present something about luminescence in science and society. I will not use difficult mathematical equations, so I keep it a little bit, so that everybody can understand it, a lot of pictures. So let me first introduce a little bit about myself. I'm from, as Professor Tanabe already mentioned, from the Netherlands. It's a small country in Europe, it's here. And if you compare it with Japan, I have plotted on the same scale here, the Netherlands fits in between Kyoto and the Fuji mountain. So you have an idea about the size, but we don't have mountains. Everything is very flat. So that makes it a little bit better populable. So we have about 17 million inhabitants. And my university is at Delft. It's a small city near the coast of the Netherlands. This is Amsterdam, and this is the harbor of Rotterdam, and this is The Hague. These are the biggest cities of the Netherlands. Delft is a small historic city center. It developed in 1600, I think. So you have typically these type of buildings with a lot of canals and bridges to give an impression about my city. And in the south of the city we have the university campus. This is our library. A lot of students always gather to sit in the sunshine. This is our auditorium for big lectures. And this is my institute, the Reactor Institute at Delft University. It's part of the Faculty of Applied Sciences. And we have an institute, a nuclear reactor. Here you see the light coming from the reactor. It's a rank of light. It's a reactor not for generating power, but for research. So it produces positrons, it produces neutrons, and we use these neutrons, for instance, for X-ray, or for neutron diffraction studies of materials, and also the positrons can be used for studying defects in materials. Now, if you look at the Netherlands from above, it's all very flat. If you're landing on Schiphol Airport in April, you might see the famous tulip fields, all the colors. But often you will see this picture, a lot of green lands and with thousands of canals. And that is because half of our country is below sea level. So if you land at Schiphol Airport near Amsterdam, the plane will stand on the ground minus 4 meters below sea level. So that means also that all the rain that falls in our country needs to be pumped out. Otherwise we will simply drown. So in the past we built a lot of these windmills to pump the water from the country into these type of canals. This is a picture of the Netherlands during winter time when the canals freeze, and sometimes the conditions are so nice that you can do the national sport of the Netherlands is by skating on the ice. And you can do long tours of 10 kilometers or 20 or 100, whatever you like to do. I also like that. These are some of my friends when we were skating on the canal, and that's myself with all the windmills. So to give you an idea about my country. Okay, about my presentation of today, I will a little bit tell you about the history of luminescence, how it has been important for us humans, what is it, and half of my presentation today will be about scintillation crystals. These are crystals, can be a few centimeters in size, that are used for detection of ionizing radiation, gamma rays, neutrons, beta rays. So I have two parts in my presentation today. So luminescence, or light, we have to distinguish between light and luminescence light. In the past, the scientists called light from glowing hot materials, like a flame, they called hot light, and light from cold materials, they didn't know about photons, they used to call cold fire, hot fire and cold fire. Now hot fire means in our modern day society we call that incandescent light, and cold fire we call luminescence light. Now the most important light source for us is of course our sun. It has been shining for 4.6 billion years, and it took quite some time before the people developed and that we were able to control fire. And about 500,000 years humans used fire as a torch to illuminate the caves they lived in. Then it took a long time before they invented something else, the oil lamp. So you have oil and that's giving light. It took another 7,000 years to invent the candle. And only 300 years they invented the gas lamp. This lamp is in my house, this is my house, where I have an old gas lamp. It's not burning on gas, there's now a modern day lamp inside. But that was about 300 or 200 years ago. And then of course we have Thomas Edison from the United States, a famous engineer who tried a lot of different things to make an electric lamp. So this is the light bulb invented in 1879 by Thomas Edison. It contains of a tungsten wire, and you put a current through, and then the wire gets very hot, and if something is very hot, it starts to emit light. Now this is the early version. This is what you know today, the famous lighting bulbs. You can see the wires which become hot and then start to emit light. And this another version is the halogen lamp. So these are all examples of incandescent light. If you go to the shop and if you buy a lamp, you can see on the packaging some units lumen per watt. And lumen per watt tells you about how bright the light is per how much energy you put in, how much power you put in. And to understand this unit, you have to understand how your eyes function. This is the sensitivity of the human eye as function of the color of light. So the human eye is most sensitive at the green part, and that's a wavelength. We express the color of light in a wavelength of 555 nanometers. And we can also see blue colors and red colors, but our eye is less sensitive for those colors. Now, the maximum brightness of a light source is when the light source emits where our eyes are most sensitive, 555 nanometer. And the luminous efficacy, that's expressed in this unit, can never be better than 683 lumens per watt. That is when you have a light source emitting at 555 nanometers, which is 100% efficient. So if we want to develop light sources, we can never go better than that number. And this is then defined as 100% efficient light source. But of course, this is a green light source, and in our rooms you want to have a white light source. So a light source needs to emit white light. Now, and what is white light? If you look at the emission of the sun, this is the emission spectrum of the sun. This is then the wavelength, the color, and this part is the part that we can see with our eyes. And only because you have a combination of colors, blue, green, all the colors of the rainbow, if you have all the proper combination, then we see white light. So the light that we here see is white light, but actually these lamps are emitting different colors so that we see it as white light. So we know that 100% efficiency is green light at 555 nanometers. If you now look at how efficient, how bright other incandescent light sources are, then our sun has an efficiency of 13.6%. That means that all the energy the sun emits, 13.6% we can see with our eyes of the energy. A candle is very inefficient. Only 0.04% of the energy a candle uses is used for light. The gas mantle is much more efficient. It's about 3 times more efficient. This is the light bulb. It's 2% efficient, so much better than a candle. And this is the halogen lamp. It's 3.5. So these are the most efficient incandescent light sources available today. But even for the most efficient light source, all the rest is just heat and is not visible. So actually it's a very inefficient way of producing light. And the scientists have been working on new ideas, new concepts to make more efficient light sources. Because a great deal of the energy consumptions in the world and in Japan is from generating light. So if you can develop more efficient light, you save a lot of energy. Now this is incandescent light. So let's now go to the other form of light, luminescence light. What is luminescence? Luminescence is caused by electronic transitions. That means an electron jumps from one state to a higher energy state. And then it falls back again, and then the energy, this is the energy, is released as a photon. So to have an efficient light source, we need first an efficient power source to bring the electron up, and then we need an efficient mechanism to bring it down again. So this gets you the photon. Now, nature has found its way to make luminescence, bioluminescence. Then excitation is by means of a chemical reaction inside the insect or the animal. So this is, for instance, a firefly. I don't know if you have them also in Japan.
Yes.
Yeah? Okay. This is the glowworm. It's not a worm, it's actually an insect. This is luminescence bacteria you can find in the ocean. This is a picture, this is from a leaflet from the bioluminescence bay in Puerto Rico. I don't know if you have been there.
We have a squid, luminescence squid.
Oh, that's one of these, perhaps luminescent squid, okay. These are from the deep ocean. So perhaps you can find them here in the Mariana truck in front of the coast of Japan, I don't know. But they use luminescence to catch other animals. So this is bioluminescence. We also have gas discharge lamps, an efficient way of producing luminescence. This is a glass container with mercury vapor. If you create a current of electrons through the vapor, then electrons will accelerate, will hit a mercury atom. The electron will go up, will go down again, and then it emits, in this case, blue and ultraviolet light. It's a very efficient means to produce lights, much more efficient than using heat, because everything stays cold. This is another type, a sodium vapor. So you have sodium in a vapor, and then you have this yellow emission. And this is actually what we have outside in the street lamps, the yellow light from the street lamps. And if you compare, so these are the efficiencies of incandescent light sources. If you now put a street lamp, we see that it has a very efficient emission. So it's 3-4 times more efficient than a halogen lamp. But of course, that's why it's used for street lamps. But of course, it's not white. Nobody of us likes to have a lamp like this in our house. So it's not white. So we have to find ways to make it white. And then we come to luminescence phosphors. If you take the gas discharge in a mercury lamp, what you can do, we can cover the outside of the lamp with a set of 3 phosphors. One phosphor emits in the blue, it absorbs the emission from the mercury vapor. Then the mercury light excites the electron, and then it falls back. It gives blue light in this phosphor, green light in that phosphor, and red light in that phosphor. And if you have the proper combination of red, blue, and green, you get white light. And this is what you have in these tube lighting. You have a combination of 3 luminescence phosphors. You have a mercury discharge, a mercury vapor, electric current, and that is how these lamps work. Now let's look at the efficiency of these lamps. This was the sodium lamp, but then the color, you have only one color. And that's the fluorescence tube. So it's pretty efficient, not so efficient as a sodium lamp, but about 12 to 15%. But it's 6 times more efficient than a light bulb. But then we have these very big tubes in our house. We don't like that either. We want to have a small light source. It's efficient, 12%, but still 82% is lost. Yeah, so perhaps we can go much higher. Now then I have to show this picture, a famous scientist, Professor Nakamura from Nitsha Chemical Industries, who invented in 1990 the indium gallium nitride light-emitting diode. It's again a different principle of generating luminescence. We don't call this luminescence anymore. With luminescence you excite the electron and then it falls back. But here you have a different principle. It's some sort of semiconducting device. You inject electrons from one side and holes from the other in semiconductor physics. And then they meet each other at the junction of P-type and N-type semiconducting materials, we call that. And at the junction, the electron recombines with the hole, and then you get a luminescence. So different principle, but it's very efficient. Again, you have one problem, you have only one color. That's the blue color. So we have to do something to use that efficiently. And what is then done is, just like these lamps, to cover the LED, the light emitting diode, with phosphorus. So you can use, and the LED is blue, so if you can use with a green and a red phosphor, you have blue, green and red, and again you can make white light. But actually nowadays the yttrium aluminum oxide is used, doped with cerium 3+, because this is then the emission from the LED itself, and this is the emission from the cerium 3+ luminescence ions inside that host material. And then you get different luminescence, but the distribution of the luminescence is a little bit over the sensitivity curve of your eyes, and you get the impression of white light. But actually, if you use this material, the light is a little bit too blue, and then we find it a little bit too cold. So we like to have a little bit warm light. And this can be done by, and this is all scientific work of the past years, by mixing a little bit gadolinium in the compound, or a little bit gallium in the compound, replacing aluminum by gallium, a little bit. You can a little bit tune the emission. And our eye is very sensitive to very small variations, so by very delicate tuning of these emission colors we can produce white light LEDs. To give you an idea about how efficient these are, this is a chart from the United States Department of Energy. It shows how light sources developed over the years and how efficient they are. So if you have the light bulb, so it's the lowest one, it's only 2% efficient. If you have the fluorescence tube, and these tubes, they're about, the best are about 70% efficient. And this is the compact fluorescence. But okay, about here it stops at 70% efficiency. And these are the LEDs. They improve much with time. And if you look at the latest developments, this was launched by Samsung, the LED. This LED was advertised by Philips, April this year, 30% efficiency. It's a lab version, it's not on the, you cannot buy it yet, but it shows how rapid these developments are. And this is an announcement by Cree last year about 250 lumens per watt, about 40% efficiency. I don't know if this is white light, it can also be a little bit colored, but anyway, you see how rapid the development is going in this field. And actually here is about the theoretical limits. So the aim in our field is to develop a LED phosphor combination that has this efficiency, and then you are about 3 times more efficient than these tube lighting. Okay, that's what I wanted to tell about development of light sources. In luminescence we make use, this is a periodic table of all the elements. We often make use of these elements. These are the so-called lanthanides. It starts with lanthanum, there are about 14 of them. It ends with lutetium. And these are very famous for the luminescence. You see some applications of lanthanides, and the light it falls now on your eyes at this moment comes from these tube lighting, and this light is made by the lanthanides. So at this moment, you see light coming from emissions in those lanthanides. So it's in the tube lighting, but also in the screens of your laptops or other screens. Often you see these emissions from the lanthanides. Now, why are they so good? The lanthanides have, each cerium to yttrium have many different energy levels. So levels where the electron can jump to. And some of these, for instance, if you excite an electron up and then it falls down, this emission is a red emission of europium. And this is the emission that comes from one of the red phosphors in these lamps. So that is now falling on your eyes. Another famous transition is in terbium, is this transition. That transition is exactly at 550 nanometers, where your eyes is very sensitive. This is often used as the green phosphor in these lamps. So at this moment also, these transitions occur in these lamps and the photons fall on your eyes. Oops. Now you see other transitions. This is a famous transitions of erbium. We cannot see it with our eyes, it's in the infrared. But this one is used in optical communications, in the optical fibers, that all the data transport through optical fibers is done by light of erbium. Now applications of 4F emissions, we call that 4F emissions, these narrow line emissions, is everywhere in our society. We have the tube lighting, I mentioned that, television screens, plasma display panels, laser applications, then we have these crystals, and I mentioned optical fibers, optical communication, so these lanthanides are used everywhere. Now this is a picture I took from a publication by the group of Professor Tanabe and Junpei Ueda. It shows what the challenge is in science for us. This shows a picture where we have the energy levels of cerium 3+ within the band gap of yttrium aluminum garnet. This is the material used in the early generation of LEDs. And it's very important where these levels are relative to the conduction band. And what they can do in Professor Tanabe's group, they can probe with photoconductivity experiments, they can excite the electron from here into the conduction band and then apply a field and you can measure the current, so you get information on where these levels are. They can also do it with thermoluminescence excitation, another technique. And also they have the expertise as a chemistry group to play with these compositions. If you replace a little bit of aluminum by gallium, or you can play with this and you can change these band gaps and you can tune the emission of the colors. So it's a very nice combination of techniques and methods to study those materials. Now we in Delft, I worked 10 years now, perhaps longer, also try to understand where these levels are. It's a complicated picture, but I do it more with some theoretical modeling and other models. And I think the nice thing of this of my visit to this group, that I learn about techniques and about the ideas in a group of Professor Tanabe, and that they can learn from me. Every Monday I give a lecture for the students about lanthanide luminescence. So I hope that we can share our knowledge and with the aim to bring the level of science further and further, of course. So we have in the lanthanides we have 4F emissions. We also have 5D 4F emissions, other type. I will not explain it in detail, but this is also used for many applications. And I like to go with these applications. Application as a scintillator detector and as an X-ray storage phosphor. This is a topic I have been working on, I think now 25 years at TU Delft. So we'll give you a little bit an idea of what it is about and what we achieved over the years. Now, scintillation crystals are real crystals, can be this size, transparent. And the idea is that if you have ionizing radiation, that the crystal stops the radiation and then the radiation, the energy, is converted into light. That's the idea. They're used many different places. Security. If you go to the airport, you have to check the luggage. They use X-rays. Okay, you need an X-ray source, but you need also detectors to detect them. Now, this is done with scintillators. If you want to know what is inside your body, you have to look through, you need X-rays. You can also use gammas, and again, you need to detect the X-rays, and then you need these scintillation crystals. Now, also in industry and science, we want to use radiation. Space exploration. There's a lot of radiation in outer space, so every satellite that goes into space, of ESA, of I think also Japanese satellites, they always tend to carry a radiation texture to detect the radiation. And we have high energy physics. 1 year ago the Higgs boson was discovered at CERN in Geneva. Now, then you collide a proton and antiproton with enormous amount of energy. A lot of particles and radiation comes off. You have to detect that. And this big detector, it is much bigger than this room, contains, I think, 110,000 23 centimeter long lead tungstate crystals as a detector, but also many other detectors, but also scintillation detectors. Now, how does it work, a scintillator? We have ionizing radiation. It can be a gamma photon, a neutron, or a very fast moving particle. It has a lot of energy, expressed in electron volts. So suppose you have 1 million electron volt. Then these particles have to be captured inside your crystal. The particle is being stopped, and when they stop, they produce an ionization track. It's a little bit illustrated here. The particle is coming from here, and a lot of electrons are excited to higher states. That's called an ionization track. Now, these tracks can make damage in the body. That's why ionizing radiation is not healthy, because you excite a lot of molecules to a higher state. Okay, you make an ionization track with a lot of electron holes, and then you have in the crystal you have luminescence centers, and each electron and hole produces a photon on the luminescence center. And since a photon, so a light particle, is typically 2 to 3 electron volts energy, we put in 1 million electron volt, so you can get out typically 50,000 photons, and they are emitted in a very rapid flash of light. So duration is maybe 1 microsecond or 20 nanoseconds. So within 20 nanoseconds you can get 50,000 photons if your scintillator is hit with a radioactive particle. Now we distinguish 3 phases. First of all, the interaction phase, and now a little bit physics. Interaction phase, the incoming particle with a high energy kicks out the electrons from the so-called valence band and brings it to the conduction band. Then we have the thermalization phase. The electron goes to the bottom of the conduction band, the hole to the top of the valence band. This all takes place in a picosecond. That's a millionth of a second time. Now then we have, in our scintillator we have our luminescence centers, and these are again our lanthanide ions. They have to capture both the electron hole, and then the electron jumps back to the hole, we get a luminescence, we get a photon. So this is how it works. The history, scintillators are already very old. First scintillators were used in the year 1900 by Ernest Rutherford. In his lab they discovered the alpha particles, and he used young students like you for that, because these young students had good eyes and they could see with this device, they could see the flashes of light coming from the phosphorus. So experiments in those times was a student looking with his eye and counting the flashes from a phosphor. That is how alpha particles were detected. Scintilla means is Greek word for flash, so a flash of light. Now after 1900, long time no developments until the photomultiplier tube was invented. And the photomultiplier tube is a very sensitive device to detect photons, much more sensitive than our eyes. And then you get a development of scintillation crystals. Well, the first crystals discovered was sodium iodide doped with thallium plus as a luminescent center by Hofstadter. And still today, this is the most used scintillator. So it has been a very important discovery. Now and then new scintillators are discovered. This is lead tungstate that was used for discovery of the Higgs boson. And I started with scintillation research around 1990, so that's about here. And 10 years later we discovered our own scintillators at Delft, and of which the most important is lanthanum bromide with cerium. We patented the scintillator, and the company Saint-Gobain in France now grows these scintillation crystals, and you can buy them on the market. So it's a commercial product now. This shows typical examples of scintillation crystals. They can be quite big. After they have grown, often they have to be put in a special shape. This is a gamma camera crystal. It's a sodium iodide thallium crystal, about this size. And it's used for imaging in hospitals, the body with X-rays. So such a scintillator, big scintillator, is about 61 photomultiplier tubes are put on the scintillator. And when an X-ray comes in, or another ionized particle, the precision of the interaction can be measured by these photomultiplier tubes, and then you can make an image of the patient with these devices. Here you see, this is my former professor, Professor Karel van Eyck, at a crystal growth company in Russia. And you see how this is sodium iodide, how it has been grown. You have the material, you first melt it, and very slowly, it takes maybe 3-4 weeks, you can pull a very big crystal. You see, this is the crystal, the single crystal out of the melt. And then this crystal is cut into slices to make these gamma cameras. Now a little bit about our discovery. With scintillators, this is actually what we call a pulse height spectrum. From a scintillation crystal you get these light flashes, and if you display the intensity of the light flash on this direction, and here the frequency, how many you have counted. That's called a pulse height spectrum. And this is a pulse height spectrum of sodium iodide thallium crystal with a 137 cesium gamma ray source. This source emits gamma rays of energy 662,000 electron volt. And when this is detected in your scintillator, it produces a flash of light which gives a signal and this, and then you can calibrate the axis. This is at 62 kV energy. Now this is sodium iodide thallium, and you see that the width of this peak, that's the resolution, the accuracy with which you can detect the gamma ray from this source. That's about 6.5%. Now this is lanthanum bromide cerium that we discovered then 10 years ago. You see now the width, it's much narrower. It's 2.9%. So that means that with this material you can determine the energy of your gamma photon more than 2 times more accurate than with sodium iodide. And also this is the decay time. This is 17 nanoseconds. Cerium has a very fast decay time, so it's 15 times faster than sodium iodide. It's also much more expensive to make it, to grow it. So that's why this is still very much used. And this is used for special applications where you need this high resolution or where you need the very fast response. Now these materials are hygroscopic, so we did studies of these materials inside a small quartz tube. The crystal is inside here, so it's a few millimeters big. So that's where we did the studies on, and we studied the properties. And this is then, now it is good, and this is then commercially grown by the company. This is the first prototype, 1-inch size crystal, and this is a bigger crystal of 4-inch times 6-inch. So it's about this size. Now people got interested in lanthanum bromide, and Philips Medical Systems, together with Dr. Joel Korb of the Pennsylvania State University in the US, they tried to make the first prototype positron emission tomography scanners. In modern hospitals you can find these scanners they can image the interior of your body by injecting a radioactive substance in your body, and then you can measure from the outside where the radioactivity goes, and you get information from the patient. But this is the first prototype. It contains 88,800 crystals of lanthanum bromide, all very small crystals around. This is then the patient, around the patient. Yeah? Now this is the first image of a patient scanned with, this was a volunteer student. So this is the images you get. You can see where the activity is distributed in the body. And if you have a tumor, then often the activity will concentrate on the tumor, so we can use this for tumor research. Now this was a prototype. The company did not go further with development. It's too expensive, so they have other crystals that is better, but it gives you an idea about how these materials could be used. It is being used in radionuclide identification. I think especially important now in Japan with the Fukushima accident. That people like to know about activity. So, and these are very small handheld monitors. You can hold them in your hand with a lanthanum bromide detector, because it has such a good resolution. You can identify what isotopes are present. It's also used for security at airports and to look for smuggling of radioactive material. The European Space Agency was also interested in this material, and 7 years ago we started a project with the European Space Agency to test whether lanthanum bromide can be used for their mission to the planet of Mercury. This is Mercury, the planet most close to our Sun. And ESA is interested, the scientists, in what gamma rays come from the surface of the planet. So they want to have a radiation detector in a satellite that orbits the planet. And why are they interested in these gamma rays? Because the gamma rays come from isotopes, and if you know what isotopes are in, you know the composition of the planet, at least the top layer. And now there are different models on how our solar system was formed, and some models predict, for instance, a lot of iron or a little bit iron, and by measuring these gamma rays you can determine if that is true or false. So that's the idea. So here you see a simulated spectrum. This is the energy scale they're interested in, 0 to 10 million electron volt. 10 mega electron volt. These are the gamma lines that they expect from different elements. These narrow peaks are measured with the best gamma ray detector available. That's a high purity germane detector. The red one is from sodium iodothallium. You see that all these details cannot be seen with a sodium iodothallium scintillator. And the blue one is from lanthanum bromide, because it has this better resolution. You can still resolve these peaks. And based on this, ESA decided to fly lanthanum bromide to Mercury. We also did a lot of tests in Delft to see whether the properties of the materials remain good when you are bombarded with protons. Because if you have a mission close to the sun, and if there's the eruption of the sun, a lot of high energy protons will go to your scintillator, and you have to be certain that the scintillator will still operate properly then. Now this is a picture I took at the testing hall. It's in Noordwijk in the Netherlands. There is the ESA center to test the satellites. So here the satellite that is going to be in orbit around Mercury is going to be tested. On the other side there is the lanthanum bromide detector. The satellite contains of more elements, 5 elements. So this is the entire thing that goes on the rocket into space. You see him again, and on this is this device mounted, and inside here is then the scintillation detector. This is the lanthanum bromide crystal, The size is 3 inch by 3 inch, and this is the photon multiplier tube to detect the photons. So we didn't make this. It was made by Russian scientists. And we only tested the material. Now the Russians also decided already before Asia did this mission to put also a lanthanum bromide detector on their satellite that was going to be sent to Phobos, a planet around the moon around the planet Mars. And the idea was that this satellite was going to land on that moon and then also detect the radiation. So this was launched in 2011, 2 years ago. But unfortunately, perhaps you have heard it in the news, there was something wrong with the propulsion, with the engine, and the entire satellite crashed in the jungle of South America, in the Amazon, in October 2010. So it fell back on Earth. So that was... Now the idea is that the Bepi Colombo, this is called the Bepi Colombo mission. The idea is it will be launched in 2014, next year. But I heard that there are some technical problems with other things, so probably it will be delayed a couple of years again. Anyway, it's nice to see that your invention is being used in these type of applications. Now this is my final slide. It's about the latest development. I showed you the spectrum of sodium iodide thallium, the spectrum of lanthanum bromide, which is 2 times better. And this is the latest developments. We succeeded in further improving the resolution. Here we have 2.9 and here we have 2%. And we did it by co-doping lanthanum bromide with cerium with a small amount of strontium 2+ or calcium 2+. A small amount gives a very big improvement. And the reason for that is, and it's shown a little bit here, this shows the efficiency of the scintillator as function of the energy of X-rays and gamma rays. This line is 100% efficiency. This is lanthanum bromide cerium, and what you see here is that it gets less efficient if you have low energies. And by co-doping, you see that it becomes very straight, and that is the reason, I can't explain it in detail, but that the resolution becomes much better. So now the next years will study from what is the effect of these co-dopants, what is happening inside the materials that can explain this much improved performance. Okay, this is my summarizing slide. Luminescence phosphors. First phosphors were made in 1612. Scintillation crystals, the first scintillators were made in 1900. So have been studied for many centuries. So you could say old science. But then I have to deny it. It's not old science because recently with modern instruments, technology and models, we get more and more in-depth knowledge about what is really going on in these materials. And actually what we see now happening is that the performance of phosphors and of scintillators is pushed towards the fundamental limits. We have control about materials and we can push them until we have the fundamental limit. And we have now the LED phosphor combination, so a lead plus a phosphor. It's moving towards 250 lumens per watt, and that's the maximum what is possible. Scintillation crystals, we have now found here 2%, and if you do a calculation, the theoretical limit is about 1.6%. Yeah, if everything is optimal. So we are also approaching that limit. So we see that by science we still can improve things that are already hundreds of years old. And I hope I've demonstrated all the many applications of scintillators and phosphors. They're very important. We don't realize it. We see all these photons every day. they're very important in science and society. And with that statement, I would like to thank you all for listening to my talk.
Thank you very much. Yeah, beginning from the history of writing by human beings, Professor Pieter Dorenbos described the development of writing from the fire, candle, incandescent lamp, and various fluorescent tube, sodium lamp, and invention of LED. And he explained how efficient the LED combination with phosphor and many applications of scintillator detection of radiation such as X-ray, gamma ray, neutron, and talked about fascinating application not only for medical application but also for searching for the mystery of the planet in sun orbiting around the sun in space, searching for mystery in space, and concluded the science of luminescence. So now this talk is open for discussion. Maybe the later part might be a little bit difficult for the student of social science, but question is welcome for all part of his talk. So please, anybody.
Thank you for precious. Thank you for a great talk.
Thank you.
Your group has discovered many new things. So, what do you think? What is the important things is to discover new things?
Of course, you can discover different things. You can discover new materials. You can also discover new mechanisms and new knowledge. So I think it's also personal what you, as a scientist, like most. Some scientists, for instance, I like to discover about how things work, about the mechanisms. And some other scientists are much focused on trying to find a new material for an application. Yeah? But finding a new material for an application is actually quite difficult. First of all, you have to have a new invention. Then you have to write a patent. And I think 95% of the patents will never become a product on the market. So often you can patent things, but in the end it will not be used because there's so many different aspects of an invention. It should be not too expensive, these scintillators, otherwise nobody will buy it. It should be perform good, it should be many different things. So yeah, it depends a little bit on the person you ask it, I think, what answer you will get. If you, about what is most important, the invention, what's the most important of the invention. Yeah, but for me, the invention of lanthanum bromide was, and is still the biggest discovery. It brings some money to my group for research, so that's also always important. You can give presentations, you can show nice pictures of satellites and so that's also important. Yeah?
Please.
Can you show some picture of the scintillator, and I think most of them are single crystal or glasses. So is there some scintillator material that are not transparent?
Now, a scintillation crystal, because you create light inside the material, it must be transparent for the light that is being created. Yeah? And
transparent is transmission for visible light, but scintillator is absorption of X-ray.
Or gamma rays, yes.
Or gamma ray.
So you need to stop gamma rays, you need to have a big volume. Otherwise, gamma rays will just go through. So you need to have a big volume, and the gamma ray will be absorbed somewhere, and there it generates light, and then the light has to come out. So that means the material must be transparent. So we can make transparent materials by growing a crystal, but that is expensive and takes a long time. If you could have other techniques, and a lot of people work on that, like ceramic, what you also do sometimes this group. If you have a material that you can grow as a powder and then press it and heat it so that it becomes transparent, then you have a much easier manufacturing process, and that also people work on that idea. And sometimes also on glasses. Depends on the application. And glass is low-cost production. So, and also plastics are being used for particle detection. So there are many different materials that can be used.
You have shown the picture of large single crystal of sodium iodide.
Yeah.
It looks for me white, not transparent.
Yeah, that's a surface.
Oh, only the surface.
Yeah, that's the surface.
If you cut it,
Yeah,
transparent.
yeah.
Okay. I see.
And the outside is a little bit powder-like. So
That's
yeah,
already.
yeah.
I see. Other questions?
What is the life of these crystals? Means these radiations may defect.
Sorry?
Some permanent defects in the crystals. These radiations,
Yeah.
they may make permanent defects in the crystals.
That's important. We have to test the crystals for that. Some crystals are we call it radiation hard. Lanthanum bromide is very radiation hard. We put it in a cobalt source to get a lot of radiation, and then look at the performance. So, but other materials like barium fluoride, you create a lot of defects. So it depends on the material. So you can have a very good scintillator, but then if you have a high radiation dose, it can go down. It's possible. Yeah.
I have a question for scientific part. And you showed the lanthanum bromide doped with cerium-3 plus and strontium.
Yes.
That's the scintillation response over 100%. Is overcome 100%. I cannot understand.
Oh yeah, that's a matter of how we define it. I understand. You mean this picture? Yeah. That the response becomes higher than 100%. But that's because we defined 100% as the response of lanthanum bromide at 62 kV. It's a matter of definition. So it's an arbitrary. Perhaps you can also define the 100% at this point. So it depends on what reference you use. So
the reference was not perfect.
the reference was not perfect.
Okay.
Yeah. So perhaps now we should make this our reference.
You should.
Yeah.
Probably there may be other question in early part. Maybe for many students, the history of writing of human beings at the early part may be interesting for you. So maybe other students are also, other questions are also welcome.
When the Netherlands people use a pump
To get a water.
to pump the sea, when the Netherlands people start use the pump.
The region of the Netherlands that I come from,
Very early part.
that's 2,000 years ago.
Yeah,
2,000 years ago.
2,000 years.
Yeah, not me, but where my... So it was inhabited 2,000 years ago. And if you go... Oops. If you go to this part of the Netherlands, where I live, 2,000 years ago, if the sea levels high, then this country would flood, would be underwater. So the villages here are built on artificial hills, about 8 meters high, and there you have the church and some houses. So people in this area, and also here in the northern part of Germany, they built the villages on a small hill, so that if the ocean flooded, they could still, they're a few meters higher. And later, that was about 1,000 years ago, we build dikes. Yeah? So this is a dike. So here are dunes, and this used to be an ocean, part of the ocean, but we built a dike here. Yeah, and then we pumped out this, so this is all land that is on the bottom of the former ocean. So because there was a dike around this ocean and now we had a flood here in this part in 1953 where 2,000 people were killed, and since then the regulation is that all the dikes around the country should be 13 meters higher than sea level. Yeah, so yesterday we had a big storm in the Netherlands, a hurricane storm here, but these dikes were strong enough to keep the water of the ocean out. And also there are big constructions here, because the rivers go to the ocean here. So there are big constructions here also to keep the ocean water out. And the point is with the Netherlands, you can see it here. If you have a storm from the northwest, then all the water will pile up because it's very thin here. So then the water will be extra high. So and then we have to, it becomes a little bit dangerous, but okay. We lived with this for 2,000 years. So and the pumping started when the technology came, and I think that was, so first we built dikes, and with a system of using the natural flow of water to the ocean. And when you have low tide, because we have quite big tides between low tide and high tide. At low tide you can open the valves so that the water goes out, and at high tide you close them again. And I think the mills started in 1600 or so, the water mills to pump. These windmills, yeah, to pump. These things. And the first ones were constructed in 1600 or so. 600? So 400 years ago. Now these are only 100 years old, but yeah.
So people use these windmill.
Oh, it's now for tourists, for Japanese tourists. Yeah. Now we used steam engines. Steam. Yeah. And 100 years ago, and then I think 60 years ago, everything is electricity. So we pump it out. Yeah.
So other questions? Maybe, yes.
Well, I would like to ask you about the government policy about science. And this may be the question for both of you, but it may be difficult for you to compare the government's policy to promote science in your country and Japan, but through the conversation between two of you, do you see any particular characteristics of the government's, the Dutch government's policy to promote science, or do you see any difference between those of Japan and that of your country?
Yes, in our country there is now a shortage of laborers, scientists, in the technical science. Yeah? So the government likes to promote students to do technical studies like engineering and physics and chemistry, of course. So that's a little bit a problem now. Students often choose for other topics, like perhaps they can make more money, perhaps, I don't know. I don't know the reason. But also physics, mathematics is difficult for many students. So that's also a reason. Not everybody can do this. The government is active in promoting universities to give better education, so better teachers, to try to motivate students better, so that students also, it used to be that students could spend 8 years at the university, and now they should finish much quicker, 5 years. So to promote students to perhaps to work harder or to be more efficient.
Well, in case of Japan, the university have difficulty teaching the subjects in English because we are the Japanese society. But in your case, you don't have that problem, right? You can attract a lot of students from overseas.
Yeah, and also all the lectures in the master's phase, so the bachelor phase is the first 2 years. Those lectures are in Dutch, but the master phase, this is all in English. So all the lectures and all the textbooks are in English. So and of course, people in the Netherlands, the Netherlands is a small country, so we have a big abroad. So all the programs are also in English on television, subtitled in Dutch, but children at a very early age learn about English, computers also. So English is no problem in the Netherlands. It's always a complaint for students in the Netherlands who wants to learn Dutch. If they try to speak Dutch in the Netherlands, the Dutch people always recognize, okay, it's not a Dutchman, so they switch automatically to English. So students complain about the Dutch people that they always go speaking English when they hear.
No more questions? Maybe students. Yes.
Sorry, I'm actually not really from a science background, so my question may sound a bit stupid. But I think in the first few slides you mentioned about the early model of the light bulb and the modern one. And I noticed that it looks like the shape of the light bulb is a little bit different. So I was wondering if the shape actually influences the amount of light that goes through the light bulb so that we have our modern light bulb as we see now.
Good question.
Yeah, I think it's a good question. It's called how, it's very important also in LED, how that you can all the photons get out. If the shape is not good, the photons can be trapped. I think the shape of this light bulb is given by the technology in those years. And you had glass blowers to blow glass, and I think the shape of this one is it's a combination of what the technology had at that moment, but the shape is not much different. I would say I think the shape of this one is almost the same as this one, apart from this thing, but it's still the same principle. You have here something, and then you have the wire. Here is something, you have the wire. So of course it's a different technology in 100 years. I think that's the reason.
Because I heard some people, when they see the light bulb, they're kind of curious and they want to fit it into their mouth. But I saw the older one, it's impossible that you fit it into the mouth. So I was thinking, do they do that on purpose to attract people to put it in the mouth and try if we can put it back?
I've never put a lamp in my mouth. I don't know about it. I don't think so.
Okay. Thank you very much for joining. And it's now time to close. So we will have a party at room 333 from 6 p.m. So please move to the room and to have a wine party. We prepare pizza and sushi also. So please join us. Thank you very much.
Thank you.